I'm going to be re-recording part 2 of Module 7 lecture. Since way back in the day, I tried to record this multiple times, and each time my system crashed, so I never got a good recording, but better late than never. So I'm going to talk about ring strain first. So the idea when we use the term ring strain is that when you have small rings, and when I talk about rings in organic chemistry, I'm talking about a four-membered ring, which would be 4 atoms. It could be 4 carbons, it could involve an oxygen, or it could have 5 atoms, 5 carbons, it could have 6 carbons. Those are what we mean when we talk about rings. So when we talk about small rings, they're generally, I would say, relatively unstable. And there's 2 reasons for that. One is that when you make a small ring, the orbitals don't overlap the same way they would in a straight chain molecule. And then the second is when you have a small ring, sometimes the bonds get eclipsed. So let me talk about those 2 factors. When I talk about imperfect orbital overlap, the first thing I'm going to ask is, well, what kind of orbitals is each of these atoms going to have? Remember, there are 2 implied hydrogens on each of the carbons in these rings I've drawn. So if I have a cyclopropane ring, each of those carbons is bonded to 4 different atoms, so it's going to be sp3 hybridized. What that means in terms of the angles of the orbitals is that the orbitals are 109 degrees apart. Because they're pointed tetrahedrally. But if I think about the actual angle inside an equilateral triangle, these angles would be 60 degrees. If I have a 4-membered ring, those angles would be 90 degrees. And in fact, in a 4-membered ring, for reasons we'll talk about in a minute, it doesn't tend to stay planar. It tends to pucker up a little bit. So those angles actually end up a little bit smaller than 90 degrees. Well, if I think about where my orbitals are 109 degrees apart. So if I go to one of these carbon atoms at a vertex, like right here, and I draw in my sp3 hybrid orbitals, my sp3 hybrid orbitals might point out in this direction, and then another one might point out in this direction. If I go to the carbon at the bottom here, its 2 sp3 hybrid orbitals might point one in this direction and one out in this direction. Now you'll notice where they're overlapping, they're not pointed directly at each other. So there's going to be less overlap between these 2 orbitals here. My region of overlap between the 2 orbitals is not going to be as big as it typically would if those 2 orbitals were pointed directly at each other. And so because of that, those bonds are not as strong as your typical sigma bonds. So this is going to be worst in your 3-membered rings because there the bond angle is only 60 degrees. In a 4-membered ring, there'd probably be a little bit more overlap. They're still overlapping at an angle, but because it's not as because they're not pointed off to the side as much, there's better overlap in a four-membered ring. But you would still have the same phenomenon where there's not as good overlap in those rings as there typically would be. So that makes these molecules less stable than they might otherwise be. In five-membered rings, there's a tiny bit of this. So in three-membered rings, this is really bad. In four-membered rings, it's bad. In five-membered rings, this effect is going to be really small because in a five-membered ring, the bond angles get closer to 109 degrees. Not quite 109 degrees, but in five-membered rings, this effect is small. When you get to six-membered rings, you can get perfectly 109.5 degree bond angles, so it works out fine. The second reason that these rings are relatively unstable is your bonds end up eclipsed. So here I have a model of a three-membered ring, and notice the three-membered ring, those three atoms are perfectly eclipsed. On the right, I've shown a different view where I've rotated my view, and notice that on the right, that bond is perfectly eclipsed. If I were to draw a Newman projection of what this looks like, I would have my front carbon with hydrogen, bond to hydrogen, bond to hydrogen, bond to carbon, and my back carbon would be perfectly eclipsed with the front one. So in a three-membered ring, all the bonds are perfectly eclipsed. If you look at four-membered rings, they can curve a little bit. They can pucker up a little bit to relieve some of that eclipsing. So they don't end up perfectly eclipsed in a four-membered ring, but there's still going to be some eclipsing of bonds. In five-membered rings, there's a little bit of that effect. So again, it's very bad. In three-membered rings, it's bad. In four-membered rings, five-membered rings, it's minor. In six-membered rings, there'll be a whole module on this, module 9, that will talk about what happens in six-membered rings and their conformations. So the bottom line that I want you to take away is that three and four-membered rings have a lot of strain. They're going to be relatively hard to form. Five-membered rings, only a tiny amount. That's not really going to have a big effect on them. But six-membered rings have absolutely zero strain. So in general, you'll see some three and four-membered rings, but they're usually hard to form. You'll see lots of five and six-membered rings because they're relatively more stable. All right, so that's the idea with rings. The other thing to keep in mind with rings is when you make a model of a ring, you can't rotate fully around any of the bonds. I drew a Newman projection here for this 3-membered ring. There's really no freedom. In a 4-membered ring, there's some freedom. 5 and 6-membered rings have more freedom of rotation. But there's no free rotation around bonds within a ring, because in order to rotate 360 degrees around that bond, you need to actually break part of the ring. So one other point. About rings, the bonds have some freedom of rotation. But not full freedom. So sometimes in a ring, you can get things that are kind of locked in position relative to each other. And speaking of that, we'll move on and talk about alkenes. We can't rotate around the double bonds in alkenes either. We talked about this a little bit in Module 5. The question is, why can't we do that? Why can't we rotate around an alkene bond? Well, I want you to remember, if I have a double bond between 2 carbon atoms, there's going to be a sigma bond right between the 2 atoms. I'll just draw that here like this. But then my second bond is going to be between parallel p orbitals on the 2 atoms. So I'd have p orbital on the atom on the left, p orbital on the atom on the right. And in order for those to stay overlapping, they need to stay parallel. Well, if I tried to rotate around that bond, I would have to break the pi bond. So I would need to break the pi bond to rotate around this CC bond. And so generally breaking a bond takes a large amount of energy, and it's going to take too much energy to rotate around that bond. You would have to break it. So we're not going to do conformational analysis with alkenes like we did with alkanes. We're not going to draw Newman projections and talk about what's the most stable conformation. Whatever configuration they're in, they're going to be stuck in. Okay, so here's the most basic example. This would be 2-butene, and it turns out for 2-butene, because I can't rotate around the bond, it makes a difference whether my 2 methyl groups are next to each other or whether they're across from each other. So this is a kind of isomerism. We've talked about drawing isomers before, and before, when we started drawing isomers, we were really drawing what we call structural isomers, where we drew molecules that were made of the same atoms, but they were connected in a different way. These are our first example of what we call stereoisomers. These are made of the same atoms. They're connected in the same way. They have what we call the same connectivity, but they're arranged differently in space. So if you ask any atom in these two molecules, what are you bonded to? It's going to tell you I'm bonded to the same four things or the same three things as the corresponding atom in the other molecule would. They both have CH3 bonded to a CH, bonded to a CH, bonded to a CH3. The only difference is how they're arranged in space. And so we want a way to distinguish between these. And there are two different naming systems that are used. There's an older system where we'd call them cis and trans. Still used colloquially, so a lot of times we would say, oh, the one on the left would be called trans 2-butene. The one on the right would be called cis 2-butene. And you can still say that, and any chemist would know what you mean. When you get to more complicated molecules, where it's not obvious what you mean by cis and trans, because really trans means the two similar things are on opposite sides. Cis means the two similar groups are on the same side. But what if we had a bunch of different groups here? We needed a more complicated, a more all-encompassing system. And that became the E and Z system. Just if you're interested, E is a German word, and gegen, which essentially means against or across. And then Z is zusammen, which means together. So entgegen if they're opposed, zusammen if they're together. So under that system, the official name for this on the left would be called E2-butene. And the official name for the one on the right would be called Z2-butene. And the convention is to put the E or the Z in parentheses out in front of the name. So you might ask, when is this isomerism going to be possible? So if you want to know when you have to consider E and Z isomerism, then you're going to look at the two carbons that are part of the double bond. So here I'm going to identify this one in orange. I'm going to identify this one in purple. And what you want to do is ask yourself on each side, are the two groups there different? And remember, they're also going to be implied hydrogens. So let's start on the right here. On the right, I've got a methyl group and a hydrogen. Are those two different? Yes, they are. If I look at the left, are those two different? Well, here I have what I would call a propyl group and a propyl group. So no, those are the same. So in the case where the two groups on either of the carbons are the same, there's not going to be any easy isomerism to consider. So this first one, I wouldn't need to say E or Z, because if I switch those two propyl groups, I still have the same molecule. If I look at the second one, if I look at the left side here, I've got an ethyl group and a methyl group. Those are different. If I look at the right side, well, what do I have there? I have a hydrogen and a hydrogen. Those are the same. So again, conclusion here, no easy isomerism. Not that I have to consider. All right, if I look at the last one, On this orange carbon, I've got ethyl and I've got methyl. Those are different. If I look at the right side, I've got methyl, and then I've got this other group. Those are definitely different. All right, so on both sides, they were different. So here, I need to consider E versus Z. If I switch two groups on one of the sides, I would get the other isomer. So if I take this, if I switch the methyl and the ethyl group, this is going to be a different isomer. So yes, I have easy isomerism here. Notice it didn't matter that I had a methyl group on each side. What matters, I'm comparing the two groups that are bonded to the same carbon. So it's okay if I have a methyl group on the purple carbon and a methyl group on the orange carbon. That's not what I'm comparing. I'm comparing this methyl with this ethyl, and I'm comparing this methyl with this ketone group. So yes, I would have easy isomerism here. And we'll talk in a minute about which one would be called E and which one would be called Z because it's not obvious. But in one of them, the two methyl groups are opposed to each other, and the other one, the two methyl groups are on the same side. All right, so someone had to come up with rules. I think this naming system gets its name from three people. I think it's called the Kahn-Ingold-Prelog system. So to decide E versus Z, we've got to go through some rules. We're on each carbon of the double bond, we're going to assign high priority to one of the groups and low priority to the other group. Talk for a minute about what high priority and low priority are and how you determine that. So if the two high priority groups are on the same side, so Z equals when they are on the same side. So if the two high priority groups are on the same side, then it's Z. If the high priority groups are on opposite sides, then it's E. Okay. So what are our rules for assigning priority? We're going to go by atomic number. Higher atomic number means higher priority. One thing to keep in mind of the groups of the atoms we deal with regularly, hydrogen is the lowest atomic number 1, and then the next lowest is usually carbon. We sometimes deal with boron, but usually carbon is the second lowest, but behind hydrogen, and then others like nitrogen and oxygen come after that. So first we decide by looking at the atom that's bonded there, if they have a difference in atomic number, higher atomic number gets higher priority. A lot of times we're going to have ties because in a lot of cases we'll have two carbons bonded to the same carbon. When there's a tie, we have to look at what each of those two atoms is bonded to and then compare what the atoms that those are bonded to one at a time until we break the tie. All right. We keep going until we break the tie. And if you get to the end of a chain and you realize you couldn't break the tie, then you'll realize that the two groups you were looking at trying to compare must have been identical. This is best seen through examples. So let's try an example here. All right, on this left side, I am going to look at the two things that are bonded directly to that carbon. And I've got up here a carbon, and then down here a carbon. So that's a tie, carbon versus carbon. Next, I'm going to look at what each of those is bonded to. So this carbon is bonded to the one I've listed as green. Green is bonded to a carbon, which is up here. no, that's the next one, and then 2 hydrogens. So it's bonded to C, H, and H. Well, if I look at my red one down here, this is also bonded to C, H, and H. So it's still a tie. All right. What does that mean? I need to keep going. When I keep going, now I'm going to be comparing this carbon here to this carbon here. All right. So for my purple carbon, the other things it's bonded to are, well, it's got a double bond to oxygen. My rules tell me that a double bond counts as 2 separate bonds. So bonds to 2 oxygens. So my purple one is bonded to O, and H. My blue one is bonded to O. It's also bonded to C, and it's also bonded to H. All right, so now I compare the first line. There, it's a tie. Compare the second line, and oxygen wins. So that tells me that the purple one ends up being higher priority than the blue one up here. So I can declare this whole group as my high priority group on this side. Now I'm going to have to go over to the carbon on the right side and go through the same process. So I compare my groups. I'm out of color, so I'm going to have to recycle my colors on this side. I'll go with green here. That's a carbon. I'll go with red down here. That's also a carbon, so that's a tie. I've got to look at what they're bonded to. The red one is bonded to C, C, and H. The green one is bonded to O. Not O, sorry. Is bonded to C, H, and H. Right? This is bonded to 2 H's. This one down here is just bonded to 1. So again, I have a tie in the first row, but then a winner in the second row. And that's going to make this group here high priority on the right. And now when I look and say, where are my 2 high priority groups? They are on the same side. So this is going to be a Z double bond, a Z configuration. To get the E configuration, I would switch 2 of the groups on one of the sides. Okay, so I've established that this is a Z isomer. In case you were wondering, there's a lot of functional groups here that we haven't talked about how to name. So there would be lots of rules in play if we were going to give a full name for this molecule. But the full name, it turns out, is Z 6-amino 3 2-hydroxypropyl 4-isopropyl hept 3-ene-al. All right, let's talk about where parts of that name come from, just because I think it's fun to have some idea how names correspond to structures, not because you're expected to know all of this. So usually we're going to start toward the end of the name. And so my name, my root here is hept. So that means there's going to be a 7-carbon chain that is going to be my principal chain. And the end of the name here is kind of a clue. I have al at the end of the name. When something ends in al, that refers to the aldehyde functional group. So that would be this functional group right here. So the al part of the name comes there. And my chain is always going to start at the aldehyde. So that would be carbon 1, 2, 3, 4, 5, 6, 7. There would be my 7-carbon principal chain. You might say, well, there is a longer chain if I start up here and number 1, 2, 3, 4. That's true, but there is a rule that if you have an aldehyde, out of all these functional groups, that would get priority, and you want your principal chain to include the aldehyde. So you choose the longest chain that includes the aldehyde. Again, not a rule I expect you to know, but in case you're interested. So the hept part comes from those 7 carbons. And then there's the 3-ene part. This 3-ene part. That's going to refer to the alkene, the double bond between carbons 3 and 4. So 3-ene tells me alkene starting at carbon 3. And then I have 4-isopropyl. That part is going to refer to this group. That's coming off of carbon 4. 4-isopropyl. That part makes some sense. I have the out front 6-amino. I have an amine group on carbon 6, so hence 6-amino is part of my name. And then I have this thing 3,2-hydroxypropyl. So what's going on there? Well, 2-hydroxypropyl will refer to this entire group here. This is a propyl group made of 1, 2, 3 carbons. There's a hydroxy group on the second carbon. I think I'm out of color, so I'm going to need a new color for this. I'll go with this yellow. So the 2-hydroxy part comes from there, and then the propyl part comes from this whole piece there. So that's how you break down a name. Again, it's not something I'm going to require you to know all those different rules, but hopefully looking at a structure and then comparing it to a name can give you some insight that can be useful to you. I will ask you to know how to name just simple alkenes. All right, so let's talk. We already talked about where the Z part of this name comes from. But then if I had just a simple alkene, how would I name it? If I'm going to name an alkene, I would follow the same rules as an alkane, except I need to find the longest chain that includes the double bond. I'm going to change the end of the name to ene instead of ane. I'm going to need a number to say which carbon the double bond starts on. So for instance, in this example, the double bond started on carbon 3. It was between 3 and 4. So this was 3-ene to tell me that the double bond was there on carbon 3. And then we put E or Z in front of the name if there's easy isomerism possible. So let's do this example, which we can do because it doesn't require all those other rules for the different functional groups. It just has an alkene. So first thing, I'm going to want to find the longest chain that includes the double bond. And the longest chain that I can find would be 1, 2, 3, 4, 5, 6, 7. You might say I could also have gone this way and had a 7-member chain, 7-membered ring, not ring, a 7-member chain. When you have 2 different chains that are the same length, the rule generally is to choose the one with a greater number of substituents coming off of it. So I'm going to choose this bottom root because it has an extra methyl group coming off of carbon 6. All right, so I have my 7-membered chain. If I number it the other way, then my double bond would be on carbon from carbon 4 to 5. If I number it right to left, then my double bond is between 3 and 4. So I'm going to go with the red numbers here, where my double bond will be on carbon 3 between 3 and 4. So the end of this name is going to be hept 3-ene. To say it's a 7-carbon chain, there's a double bond between carbon 3 and 4. You could also say 3-heptene. So put the 3 in front of that whole name. Some people think it sounds less choppy that way, so a lot of people will do that. Then I would name the substituents. So it looks like Coming off of carbon 4 here, I have a propyl group. So 4 propyl, 3 heptene, or 4 propyl hept 3-ene. And then I have methyl groups coming off of carbons 3 and 6. So I would have 3,6-dimethyl. Oh, made it a little too tight there. 3,6-dimethyl, 2-heptene, or 3-heptene. So my final name, 3,6-dimethyl, 4-propyl, hept 3-ene for this alkene. So a lot of the same naming rules, we're just adding in a number for where the double bond is. And then I would want to say whether this is E or Z. I've got to include that out front. So on the right-hand side, I have a methyl group, or I have this group, which would be higher priority than a methyl group. On the left-hand side, I have this whole group, which would be higher priority than the straight-up propyl group. And so this is going to be a Z isomer. So my name would be Z 3,6-dimethyl 4-propyl hept 3-ene. And that's pretty much it. That's what you need to know. Let me know if you have questions.